1 from 2, this would be R2 hat. They look a whole lot alike. As a matter of fact, I got my hands on a copy of the proposed high school standards for South Carolina schools. And one of the physics criteria was that you needed to be able to get the connection between electric force and gravitational force, which if you really could do, would get you a Nobel Prize and allow you to graduate from a South Carolina high school. It did not make the final copy. Somebody caught it. I think what they were going for was recognizing that the similarity of the formulas, not being able to actually look at a connection between these two forces, because that is incredibly difficult to do. All right, so the reason I bring this up is that there's a formula for this. Sorry, try that one again. When dealing with energy, I know that for every conservative force, there is a potential energy formula. This is a conservative force, that's a conservative force. Over here, what is the potential energy formula associated with this gravitational force? This was your chance to impress me that you remembered from, well, for some of you, a couple of weeks ago. For others, a couple of years ago. No one wants to impress me. Not today. I was hoping. Just if we're playing R. The derivation requires calculus, so we're not going to go into that. But the main reason I do this, I was hoping that this would have some familiarity to you, that there is a very similar formula over here, that the electric potential energy, KE Q1 Q2 over R. There's no negative in front over here. Think about part of what the negative is telling us. Oh, sorry. Plus some constant. Plus some constant. What is the big difference between charges and mass? In terms of, I've got two masses here. What can you tell me about the force acting on them? And I have two charges here. What can you tell me about the force acting on them?
They're both kind of pulling together.
The masses or the charges?
Both.
All right, almost there. Charge is always going to be pulling together?
No, but it's in a direction relational to that. They might be pulling the opposite up together. Pushing.
So they might attract or repel?
Yeah.
Okay. Yeah. And what about masses?
They're always pulling.
Yeah. So masses will always attract. Charges might attract or repel, and that's why the minus sign shows up if they're attracting. And over here, you don't see the minus sign, but if they're attracting, one of these is going to be negative. And if one of these is negative, then this becomes negative. So a negative potential energy for these situations implies that there's some sort of attraction going on. And since we have not figured out what negative mass is, we assume mass is always a positive. Although I'm sure there's some theorist out there who's got a paper that talks about negative mass, hoping that someday someone will find it. So if I have a positive charge here, and I put a positive charge here, what's gonna happen? All right, I got the hand gesture in the back. All right, I got several people doing hand gestures. Ooh, the exact same hand gesture. All right, so they'll repel from each other. If I just take these two charges and I just stick them right there, so they start out at rest, they will start to move. I think that's what's implied by that answer I was getting from several of you. If they move, what can you tell me about the energy?
It'll decrease the farther away it gets,
What,
or the kinetic energy will decrease.
all right, this is your chance. I'm about to ask that question. Anyone who's had me before should know this. Actually, everyone should know it, but anyone who's had me should be able to do this in unison. What's the formula for kinetic energy?
1/2 mc².
Not quite the chorus of angels that I've heard in the past, but still, not bad, thank you. All right, so if they start out at rest, what is the total kinetic energy?
0.
So, if the kinetic energy decreases, which is what I think I heard you say, how does it get smaller than 0? Well, mathematically, how can this be negative?
It can.
Well, mathematically it can, physically it cannot, but mathematically, how can this be negative?
It has to be negative.
All right, so negative mass, which we're not sure what that is, or
The V is negative as well, or?
no, if V is negative, then it'll just square and that'll go away. What squared gets you a negative number?
I,
Yeah. So if we have an imaginary speed or a negative mass, then we can get a negative kinetic energy, but such things do not exist as best as we know. So, however, you were almost there. Some of the wording was off. Let's try this again. So what happens as they start moving apart? What can you tell me about the energy?
Kinetic energy increases.
Therefore, wow,
Potential decreases.
there we go. Yes, if kinetic goes up, potential goes down because
It's no longer at rest?
say it again.
Is it because it's no longer at rest? Like,
They're looking for something else. It's no longer at rest, that's why kinetic energy is increasing. But why does potential energy have to decrease if kinetic energy increases?
Because of conservation of energy,
And do we know there's gonna be conservation of energy?
because of Newton's laws.
There's another reason. What can you do about the force involved?
It's a conservative force.
Yes. And what does the conservative force do?
Conserve.
Conserves.
Energy.
Yeah. Because we're dealing with a conservative force, reinforced by the fact that there's a potential energy formula, because there's a conservative force, energy is conserved. Therefore, if kinetic goes up, potential has to go down. If potential goes down, kinetic has to go up. I think I just reversed that. Try that one again. Or if kinetic goes down, potential would increase. But then if I start them at rest, they start moving, kinetic energy goes up, potential energy has to decrease. Let's see if that makes any sense. I have two positive charges here. This is a constant, so my numerator here is some positive number. As R increases, As R increases, what happens to the potential energy?
Gets smaller.
Now, let's take it to that next step. Because I have some constant, we'll just assume it's one, so if I have 1/2, 1/4, 1/6, 100. As my denominator gets bigger, my fraction gets smaller. Now I've got a positive and negative charge. From a force point of view, what's gonna happen?
They're going to attract.
Absolutely. Now, from an electric field point of view, I got a positive charge here exuding, sliding an electric field out. The negative charge, since it's the electric field, it goes, ooh, I wonder what's that direction, and then ejects it out. But from a potential energy point of view, I got positive charge here, I got a negative charge here. If this negative charge is getting closer, R is getting smaller. But over there, the kinetic energy is increasing, so potential energy has to decrease. But over there, didn't we say as R gets bigger, potential energy gets smaller? But here we're saying as R gets smaller, potential energy gets smaller. How does that work? Have we violated physics? And the answer to that is no. Sorry to spoil it. Why is it that R getting smaller here decreases my potential energy, but R getting bigger here decreases my potential energy?
And a negative charge.
Therefore,
Numerator is negative, and then denominator is smaller, but not negative.
so if I stick a negative sign in front of these, as R gets bigger, I get a smaller fraction. Oh, wait a minute, try that one again. As R gets bigger, I get a larger fraction. That was said correctly. Negative 0.01 is bigger than negative 0.5. So, in the case of opposite charges, we've got a negative numerator or a negative fraction, and so we need R to get smaller in order for potential energy to get smaller. So we now have the situation of explaining why two charges would attract or repel based upon potential energy. So we can now explain it with forces, with electric field, and potential energy. There's one more to go. How many of you watched the video already? Okay. Let's just sort of set up a grid here. If I have vectors, let's see if I can get something darker. Scalar. Two charges. One charge. So if I'm dealing with two charges and dealing with vectors, I'm dealing with force. So this is the electric force on 1 from 2 is equal to my electrostatic constant, Q1, Q2 over R squared, R2 hat. If I have one charge and I'm dealing with vectors, I'm dealing with an electric field. My electrostatic constant times whatever the charge is over R squared, R hat. If I'm dealing with a scalar and two charges, I'm dealing with potential energy, the electric potential energy, which is my electrostatic constant, Q1, Q2, over R plus some constant. There seems to be a gap here that we're about to fill. let's take a look at units before we fill in this last blank. What is the SI unit for force? Good. SI unit for electric field? SI unit for potential energy? It's the same as for work, that helps. All right, formula for kinetic energy, as was recited earlier, 1/2 mv squared. What's the SI unit for mass? SI is kilogram. For speed? And since we're squaring that, so we end up with a kilogram meter squared per second squared. That is an SI unit. It's not the one word SI unit, but that is an SI unit for potential energy, or for energy in general and work. What is a Newton? What is Newton's second law? So a Newton would be SI unit for mass,
Kilogram,
SI unit for acceleration.
meters per second squared.
That's a Newton by definition. A kilogram meter per second squared. So it's almost the same as that, except this has an extra meter in it. So this right here is also a Newton meter. Anyone figure out the one word?
Joule,
Yes, joule. Or if you want to take it slightly more basic, Newton meters or kilogram meter squared per second squared. And now here. When we went from electric force to electric field, we basically had this assumption that something existed without that second charge. That there's this electric field being given off that existed just from the property of a charge. And so now here, we're gonna make sort of a similar thing, that there's this thing that exists just because I have a single charge. So we're gonna sort of get rid of a charge there. So I just have my electrostatic constant times Q over R plus a constant. Let's talk about units before we start labeling it. What would the units be? If it helps, think about the relationship between electric field and force. Yes, joule per coulomb. Which is too much for physicists to write, so they came up with enough. There is a one-letter version of this that we'll get to in a moment. So this is a property that exists because I have a charge here, and I don't need a second charge in order for this to exist. This is known as electric potential. Within context, I might just call it the potential. But at this point, if I want potential energy, I need to actually use the word energy. If I say, what's the potential, I'm talking about this, not this. The symbol for electric potential is a capital V. The unit for electric potential is the volt, which has a symbol of capital V. I do want to point out, I have not defined voltage. Voltage is related, but I have not talked about voltage yet, other than my disclaimer. Unfortunately, the symbol for the quantity and the symbol for the unit are the same. They're both capital V's. So in physics, I could write, and this is a legitimate physics statement, that the electric potential is equal to 3 volts. In math class, V would be equal to 0. In physics, you go, okay, I understand, that's a unit and that's a quantity. Unit. Quantity. Please do not confuse them. Again, with uppercase, lowercase, Greek, and I guess Roman alphabets, we have 100 letters, symbols. We've run out. This is one of the few units that the person's last name is not Volt, but it is named after someone else. Anyone know the person who's being honored here? Volta. His last name has an extra A at the end. I don't know why they didn't call them Voltas, but that was not part of that discussion. All right, so we've got this other thing over there. All right, so if I've got let's say a 9 Coulomb charge right here. So unit of charge, so 9 coulombs is positive. If I am, say, 1 meter away, oh, actually, not coulombs, make it nanocoulombs. That'll make the math simpler.